Hello everyone, welcome to the ITLS Academy. Today we are going to discuss the topic that is your changes to a milk component during a processing. Okay, so we all already discussed about the composition of the milk, and along with it we are already discussed the milk component and milk processing. So these three topics and this topic are what they are the interconnected. Okay, so the we these topic are already discussed and the video related to this are already uploaded in our account. You can go and check it. So here what we are going to do, we are going to see that when during the processing, okay, we all know that when we get a milk is reaches to the industry, then the processing of the milk are started. Processing of the milk started. Okay, now during this processing, obviously there is a changes in the component of the milk. Okay, which means that what happened with the fat, what happened with the carbohydrates, okay, what happened with the proteins, vitamins, minerals, all these things, how these are the component of the milk, how these component are changes when the processing of the milk are completed or during the processing of the milk, we are going to see in today's lecture. Okay, so let's start the lecture. Changes to a milk component during a processing. We all know that during a processing, what happened, we give a heat. Okay, so this heat will changes the nature and behavior of the milk component. Nature and behavior of the milk component. Okay, sometimes these changes are what they are desirable, means that they increase the quality of that milk, and sometimes they are what they are undesirable. So these changes we are going to discuss in today's lecture. Now see what is written here. Processing alter the nature and behavior of the milk component, which consequently influence the properties of the dairy product. Okay, so these changes also get affect the property of the dairy product. Means that butter. Okay, so the butter property are depend upon what? Upon the processing of the milk. Okay, now come to the next one. Now the first step is the homogenization. Homogenization simply means that the uh, reduces the fat globule size. Suppose that this is the size of the fat globule. Now during the homogenization, these fat globules are divided into a small, like small size globules, okay, like this, which increases the surface area. This is called the homogenization. Okay. Now see, intense turbulence during the homogenization markedly reduces the fat globule size. Okay, first of all, the globule size is this. Now this globule size are converted into the smaller one, means that this size are reduces with a consequent 4 to 6 fold, which increases in surface area because the amount of available original membrane material is insufficient to cover this area, because at that time the original membrane material which are available are insufficient for covering that whole area. That's why the size of the fat globule will reduces. Plasma protein adsorb onto the fat globule surfaces. Okay, so there is a plasma protein which are adsorb, not absorb. It is the adsorb onto the fat globule surfaces. Then the new membrane in a homogenized milk consists of MFGM material. Now tell me in a comment box what is this MFGM material. Then after that I will tell you what is the full form of this MFGM material. Okay, the new membrane in a homogenized milk consists of MFGM material, uh, then casein micelles, and whey protein. Okay, and it is taken by Anderson et al. 1970 and Darling Butcher 1978. Now this FMGM means that this is your milk fat globule membrane simply. Okay, now come to the next one. Casein micelles adsorb prefrontally over the whey protein, and the adsorbed casein micelle partially spread on the fat surfaces. Okay, so this casein micelles, what they do, they adsorb over the whey protein. Suppose that this is your whey protein. Now in the whey protein, this casein micelles are what they are adsorb. Now what is the difference between the absorb and adsorb? Now see, simply the adsorb means that suppose that this is your whey protein. Okay, this circle is your whey protein. Now here the casein vessels are adsorbed means that it make a bond with the surface of the micelle protein. Okay, this is your adsorption. Now absorption means that suppose that something is like this and it will absorb inside it like this. Okay, so this is a difference between the absorption and the adsorption. Now here the casein micelles, what they do, they adsorb over the whey protein, and the adsorb micelle are partially participated in the partially spreaded on the fat surface, which are possibly as a sub micelles, and it is taken by a Wallstra and Ortwegen 1982. Although the whey protein make up a much smaller portion, that is around only 5%, they cover a disproportionately greater area, about 25% of the fat globule surfaces. Okay, so um, mm, the amount of the whey protein is very important, very smaller, that is around only 5%, but they cover a disproportionately, and the greater area that covered by a whey protein is about 25% of the fat globule surfaces, and again it is taken by a Wallstra and Ortwegen 1982. The relative content of the original membrane material in the new membrane are totally depend upon the increase in surface area, thus on the intensity of the homogenization. Okay, now the next is your homogenized fat globule also act as a large casein micelles, and it will participate in any reaction of the casein, that is your ranitting and acid precipitation and heat coagulation, and it is taken by a Van Berkel and Wallstra 1989. Now the next one, after homogenization, there is a cluster of the fat globule. Okay, like this. When the homogenization are completed, there is a cluster, this form of. Okay, just a minute. Okay, cluster of the fat globule. This is called a, this is what? This is your cluster of fat globule. Cluster of fat globule which are after the which are obtained after the homogenization. Homogenization. Okay. Now, in which the casein micelle are shared by a globule may be found. So, maybe here the micelle, casein micelles are found. Okay, like this. This is what? This is your casein micelle. And it is taken by a Ogden et al. 1976. If there is a two-stage of homogenization, that is your partially, then it will prevent the occurrence of the homogenization cluster. Homogenization retard the creaming because the fat globule are smaller. Okay. In homogenization, what we do, we break the or reduces the fat globule. That's why it will retard the creaming process. Lipase is activated during the homogenization because there is a transfer of casein associated lipase on the surface of the fat globule, which increases in fat surface area and the dissociation of the casein micelles. Now the next is your heat treatment. After homogenization, what we do, we give a heat treatment to the milk. After homogenization, there is a heat treatment. Now, when we hear about the heat treatment, that means that the pasteurization. So, this pasteurization is either HT, um, HTST, either LT time, low time, HTST and LTLT, low temperature, LTHT and UHT. Okay, that means that high temperature shorter time, low temperature higher time, LTLT, or low temperature longer time, and UHT, that is ultra high temperature. So that I already told you, heat treatment are totally depend upon the combination of the temperature and time. So here the pasteurization are occur if 72 degrees Celsius, then it will come under the HTST process. 72 degrees Celsius for 15 seconds. And if the temperature is in the range of like if it in the range of 63 degrees Celsius, then it will for 30 minutes. Okay. Then the next is your UHT. In that time, the temperature range is around 132 degrees Celsius for 2 seconds. So this is the basic of the heat treatment. Heat treatment vary widely, ranging from the pasteurization 72 degrees Celsius for 15 seconds to a low temperature longer time, for example 85 degrees Celsius for 30 minutes, to a higher temperature shorter time, that is 120 degrees Celsius for 2 minutes, using a direct or indirect heat. That indirect heat, we do a steam injection, and indirect heat, we use a plate heat exchanger heating. These heat treatment cause a number of important chemical and physical reaction in a milk product, and many reaction which involve a non-protein constitute of milk as well. So some of these changes are also listed in a table which we discuss in the next slide. Knowledge of the heat induced changes in a milk has expanded a non-considerable during the last 30 years, and had a major review have been published. And it will taken from a Fox 1981, Singh 1990, 1988, Singh and Creamer 1992, Singh and Newstead 1992. A brief overview of the main changes is provided in the following section. So now we are going to discuss about the table. Now, this is a process and their effect. First process is your heating. Heating will destruct the bacteria, inactivate the enzyme, destruct the some vitamin, denature the whey protein, formation of the aggregate of the whey protein, formation of the complex between the gamma casein and beta galactoglobulin, shift of the soluble salt to the colloidal phase, changes in a mesyl structure, dephosphorylation of casein, peptide bond, cleavage of the protein, lysinoalanine, formation, Maillard reaction, isomerization, and degradation of the lactose. Also changes the fat globule membrane, and pH will decreases during the heating process. Now the next process is your evaporation process. In evaporation process, there the concentration of the milk solid, increase in colloidal salt, increase in mesyl size, decrease in pH, limited the denaturation of the whey protein. Next is your homogenization. In homogenization, there is increased number of fat globule, absorption of the casein on the fat globule, decreases in a fat globule size, also decrease in protein stability. And the last one is your uh, spray drying. Spray drying, rapid removal of the water, relatively minor changes in the protein. So this is the process and their effect on the milk and milk product. Now the next is your changes in the protein. Upon heating the milk above the 60 degrees Celsius, whey protein are denatured. Okay, so when we heat the milk above 65 degrees Celsius, then in that case, whey protein are denatured. Okay, by the unfolding of their polypeptide and thus exposing the side chain group originally buried within the native structure. Okay, so what happened, there is a polypeptide bond in a whey protein. This polypeptide bond are unfold, and when they are unfold, then the side chain are exposed, and they are originally buried with the native structure, which are originally buried in a native structure. Now they are what, they are exposed. Now the unfolded protein then interact with the casein micelles, or they are simply aggregate with the themselves. Okay, so the unfolded protein in which the polypeptide bond are unfolded, now they are called a unfolded protein. What they do, they interact with either they interact with the casein micelles, or sometimes they aggregate with themselves, and it involving a thiosulfide interchange reaction, hydrophobic interaction, and ionic linkage. Okay, so there are two type of the reaction occur. One is your thiosulfide interchange reaction, hydrophobic interaction, and ionic linkage. The order of the sensitivity of the various whey protein to a heat in milk has been reported by a immunoglobulin BSA, then then beta galactoglobulin, alpha galactolactolobulin, and it is taken by a Denberg and Kessel 1982, Oldfield et al 1988a. Now the next is there is a kinetic denaturation of the whey protein are quite complex. If we see the kinetics of the denaturation of this whey protein, they are what, they are complex, with the reaction characterization which is show a marked change above the 80 to 100 degree Celsius. Okay, so the denaturation of the alpha lactoalbumin, which are appear to follow a first order reaction, but they are what? But there is an agreement on the order of the reaction for a beta lactoglobulin that have been not achieved. Okay, Denberg and Kessel, they suggested that in 1998 that there is a reaction of 1.5 is best to fit the rate of the denaturation, but some other workers also favor either first order or second order reaction. Despite there is a difference, and there is a general agreement that the denaturation reaction can be represented by a non-linear Arrhenius plot. Now the next one is the apparent activation energies are also reported by various workers, and that is your Hillier and Lister 1972, Denberg and Kessel 1988, Oldfield et al 1988a. They are in the range of 260 to 280 kg per mole for a beta lactoglobulin and 270 to 280 kg per mole for a alpha lactoalbumin, and the temperature range is should be below the 90 degrees Celsius. If the temperature are higher, then there is a active then there is decrease in the activation energy, and then ranging from 54 to 60 kg per mole. In case of beta lactoglobulin, and from 50 to 70 kg per mole for a alpha lactoalbumin. So there are different techniques are used by our various workers to assess the denaturation, which included the measurement of loss of solubility at the pH of 4.6, then reactivity of the thiol group, electrophoretic analysis, loss of antigenic activity, and the differential scanning of the calorimetry, because these methods are totally based on a different physical and chemical properties of the protein. So it is not surprising that the data which are obtained by these techniques are not totally in agreement. In addition, various heating methods have been used, which include heating the sample in a glass tube, capillary tube immersed in a water oil bath, and a laboratory scale heat exchanger. Now the next one is your changes in the fat globule. Again, when the whole milk are heated above the 60 degrees Celsius, then the fat globule membrane are protein are denatured, which give a result in exposure of reactive thiol group. Suppose that this is your milk, whole milk. Now when we heated this whole milk above the 60 degrees Celsius, in the previous case the temperature range is above the 65 degrees Celsius, but here the temperature range is above the 60 degrees Celsius. Now in that case, the fat globule membrane protein denature. Okay. And reactive thiol group are exposed. As a consequence, thiosulfide interchange reaction may occur between a different membrane protein, and this whey protein could also participate in this reaction. Both your alpha albumin and beta lactoglobulin have been shown to bind a via intermolecular disulfide bridges to the surface of the milk fat globule when it is heated between the temperature range around 65 to 85 degree Celsius. Now the whey protein which are present in a whole milk have a affinity for the FMGM than for the casein micelle surfaces. Okay. Then the phospholipids are migrated from the fat globule to the aqueous phase when it is heated to a some extent. When it is heated to a some extent, then the phospholipid are migrated. Now the next is your when a whole milk are homogenized before the heating whole milk are homogenized, then the fat globules behave like a let's behave differently during and after the heating. Okay, suppose that when we heated the milk before, what we do, we homogenize it. So at that case, the behavior of the fat globule are different during the heating and after the heating from a natural milk fat globules. The membrane of the homogenized globule have a different composition, and the size of the globule is very smaller. The subsequent heating of homogenized milk causes a complex formation between the whey protein and the casein, which are absorbed on a fat globule surfaces. Now this homogenized fat globules act as a larger protein act as a large casein missile because this casein in their new membrane, and thus they participate in any reaction of the casein as I stated earlier. Now, when the whole milk is heated before the homogenization, this whey protein are denatured if the temperature ranges more than 70 degrees Celsius and interact with the K casein of casein missiles during and the native globule membrane. And here the pH is what? Natural, at a natural pH. Now during the subsequent homogenization, this micelle complex of a casein and a whey protein which absorb on the newly created fat surfaces. Now the next is your changes in a milk salt. Okay, so the next changes is what? In a milk salt. Milk salt exists in an equilibrium between the soluble and the colloidal phase of the milk. Milk has a two phase. One is your soluble and one is your colloidal. Okay, so this milk salt are exist at a equilibrium in both the phase, and they are and this distribution is affected by the heat treatment of the milk, but this distribution are affected when the milk are heated. Heating milk cause a transfer of the calcium and phosphate from the soluble to the colloidal state. Okay, so here in a soluble state there is a, just a minute, calcium, and the next is your phosphate. Okay, when the milk are heated, then this calcium and phosphate are transferred from a soluble phase to the colloidal phase. On a subsequent cooling, some of the indigenous or heat precipitate calcium phosphate may be redissolved, and especially if the heating temperature are less than 85 degrees Celsius. However, after the heating at higher temperature, the precipitated material does not resolubilize. Okay. However, when the temperature are high or when the milk are heated at a higher temperature, then the material which are already precipitated, it does not resolubilize. Then there is a decrease in soluble calcium phosphate citrate during a heating at the range of at the temperature range between 70 to 19 degrees Celsius, which involve two steps. The majority of the decrease take place during this first minute of the heating, after which a small decrease occur over an extended period of time, which is up to 120 minutes. Heat treatment have a little effect on a monovalent ion, that is your sodium or calcium and chlorine ion. It is known that the subsequent effect these change in a equilibrium of salt ion and have on a processing property of the milk. Changes in a lactose. Lactose can interact with the protein during the heat treatment of the milk, which involving in a Maillard reaction. This reaction involves in a condensation of the lactose with the free amino group of the protein, with the subsequent rearrangement and degradation of the leading to a variety of the brown color compound. Manifestation of the Maillard reaction, which are very important in a milk product, that is your brown color of flavor loss, available lysine, lower the nutritional value, reduces the digestibility, reduces the solubility. The rate of the reaction are strongly dependent upon the pH, time and temperature of heating, water activity and temperature during the storage. Beside of all of these lactose may isomerize into the other sugar, that is your lactulose. If the temperature of the heating greater than 100 degrees Celsius, then this lactose are converted into acids, especially the formic acid. Thereby there is a decrease in the pH of the milk. Okay, if the heating temperature of the milk are greater than the 100 degrees Celsius, then in that case the lactose are converted into a different acid, but especially into a formic acid, due to which the pH of the milk are decreases. Now the next is concentration. milk are normally concentrated by a evaporation or a ultrafiltration. Okay, so we all know that this concentration of the milk are take place by a evaporation and ultrafiltration. These are the two methods. Evaporation is normally carried out at the temperature range between 50 to 70 degrees Celsius. In addition to a concentration, evaporation causes numerous other changes in a milk system. The pH of the milk decreases during the concentration. Okay. So when we concentrate the milk, then the pH will decreases from an average initial value from 6.7 to 6.3 at 45% of total solid. This is partially due to the change in the salt equilibria as a more calcium phosphate are transferred from a soluble to a colloidal state. And this pHR decreases due to the transfer of the calcium phosphate from a soluble state to the colloidal state with a convenient release of the hydrogen ion. Lee Greed and the Bruerel in 1982 also shows that when milk are concentrated above a five-fold by evaporation, then the soluble phosphate increases by a factor above about 2. This reminder of the soluble calcium or phosphate being transferred into a colloidal state. Now the next is under a normal condition with the evaporation temperature ranges below the 70 degrees Celsius, it will alter the protein like to be a minor comparison between the incurred during the heating. Then the concentration of the skim milk by ultrafiltration result in increase in fat, protein and colloidal salt. Okay, if the concentration of skim milk is done by a ultrafiltration, then in that case there is an increase in fat, protein and colloidal salt. Okay, the ultrafiltration temperature has also impact on the composition of the concentrate with the higher temperature which give a result in higher permeation rate and lower retention of lower molecular weight component. Now the next is your examination of the casein micelles in a ultrafiltration concentration by a electron microscopy. They shows that there is a significant differences compared with the micelles in a unconcentrated milk. Okay, so the concentrated milk are totally different. The micelles which are in concentrated milk are totally different from a micelles in unconcentrated milk. In a skim milk at a volume concentrated factor of 5, the average diameter of the casein particle appear to be very smaller. Milk protein concentrate are more susceptible to a heat denaturation of a whey protein. For instance, when the heat treatment at 75 degrees Celsius for 5 minutes is applied, then there is a denaturation degree increases from 30% to 64% in ultrafiltration retention to a concentration factor about 4.4 is to 1. However, Wongna et al. 1996 also noticed that there is a difference between a beta lactoglobulin denaturation between the normal two-fold ultrafiltration concentrated skim milk. Now, next is your spray drying. So there is a little work which are reported on the changes which are induced due to the drying of the milk. Atomization of the concentrated give a large surface area which drying can take place. There is a droplets are splayed onto the main drying chamber and are intimately mixed with the dry heated air that is around 182 to 20 degree Celsius. Drying are usually very rapid and the temperature of the milk is droplet does not exceed 70 degrees Celsius until they have lost almost all their water. Speed drying is simply means that the removing the moisture from the milk. Now the temperature of the droplet approaches that of the outlet air as a drying process which are near completion. For this reason, the outer air temperature is a critical parameter which control the heat damage due to the dry milk product. The heat exposure of a milk during a spray drying may vary considerably. It totally depends upon the design of the dryer, operating non-condition, and the length of the time the powder is held before a cooling. The native property of the milk component are essentially unmodified by a moderate drying condition. The normal size distribution of the casein, micelles, and their heat stability and retenting characteristic are substantially recovered as a reconstitution of the spray dried milk. Now the next is your acidification. This milk can be acidified by the use of the bacterial culture which ferment the lactose to a lactic acid by the addition of the chemical such as HCl, or by the use of the gluconolactose, that is GDL, where the hydrolysis of the GDL to a gluconic acid which result in the reduction in the pH. Acid induced coagulation and gel formation in a milk that have been reviewed by Lucy and Singh in 1998. During the acidification of the milk, many of the physiochemical properties of the casein micelles undergo a considerable changes, especially the pH range, which is from 5.5 to 5, and it will decreases to a 5.0, which give a result that the pH of the milk is reduces, CCP is dissolved, and the casein are dissociated into a milk serum phase. Then the extent of the dissociation of the casein are totally dependent upon the temperature of the acidification. That is your suppose that when a temperature range is 30 degrees Celsius, then the pH will decreases, and it will cause a virtually no dissociation. Now at 4 degrees Celsius, about 40% of the casein are dissociated in the serum and pH will become 5.5. Aggregation of the casein occur as a isoelectric point at pH 4.6 is approached. Apparently, little changes in the average hydrodynamic diameter of the casein micelles occur during a acidification of the milk to a pH 5.0. So there is a lack of the changes in the size of the micelle on a reduction of the pH of the milk 5.5, maybe due to the concomitant swelling of the particle as a CCP is solubilized. Okay. Now the next and the last is a renate coagulation. So the coagulation of a milk by a specific action of selected proteolytic enzyme, particularly rennet, from the basis for the manufacturing of most of the cheese varieties. These rennet consist of the enzyme that is your chymosin, pepsin, and they are traditionally prepared from the stomach of the calf, kids, lamb, or other mammals in which this rennet are principal proteins. So this is about the rennet coagulation, and this is about the changes of the changes occur in a milk component during the processing. I hope you will understand, but if you have any query related to this topic, you can freely ask me in a comment box, or for a further detail you can follow the ITLS Academy on different platforms, that is Instagram, Facebook, Twitter, YouTube, WhatsApp, and LinkedIn. Subscribe our channel ITLS Academy on YouTube and get our app from Google Play, or for any query you can ask your query to the helpline number that are already mentioned in your slide, that is 7080833450. Visit our website www.itlsacademy.com. Thank you for watching. Please like, share, and subscribe our channel.